This program is presented by University of California Television. Like what you learn? Visit our website or follow us on Facebook and Twitter to keep up with the latest UCTV programs.
I'm Pat Conrad. I am the Associate Dean for Global Programs in the School of Veterinary Medicine here at UC Davis. I'm also the chair of the Planning Committee for this wonderful UC Global Health Day. And this is the fourth UC Global Health Day that we have held, led by the UC Global Health Institute, which is an institute, virtual institute, extending over all 10 campuses, encouraging faculty, students, and staff interested in global health to come together. And so we're very proud of UC Global Health Day and delighted to be hosting it here at UC Davis. So as we begin, I'd like to welcome some very special guests. I'd like to mention and welcome Dr. Hailey DeBoss from UC San Francisco, who is the director of the UC Global Health Institute, Tom Coates, who is the co-director of the Global Health Institute, and Jack Stobo, who's our head of health sciences for the system. The UC system is here. And of course, very importantly, our very own Chancellor, Linda Katehi. We have quite a number of people who are leaders on all of our different campuses, as well as UC Davis, too many to mention by name, so I'd like to welcome all of them. And I'd like to extend a special welcome to all of the students. We are delighted to see you here. You are the inspiration and the enthusiasm that really moves us forward and inspires us in global health. And a special shout out to the student subcommittee that helped to plan Global Health Day. We have representation from all 10 campuses, and it's to their credit that this year we have the largest enrollment in Global Health Day, over 400 people registered, and we also have representation in those registrants and in the posters and breakouts of all 10 campuses. So a big hand to the students and the student subcommittee, please. So we did have some faculty. We had a faculty planning committee as well. So I'd like to acknowledge my co-chair, Mark Shanker from UC Davis, and the other members of that committee, John Mazette, Steve Carell, Michael Welks from this campus, and Neil Delalakar from the UC Riverside. So very important as these events always go are the staff as well. So I'd like to especially thank from UCSF, Catherine Lee and Rawa Ngusi, without whom none of this would have come together so beautifully, and here on our campus, Elizabeth Leisure. So if we could give them a big hand as well. And we're doing that now because by the end of the day, when you're dancing to the mariachi music at our reception, we may forget this, and drinking wine and cheese, so don't forget that. What I would like to do now is to introduce our illustrious leader of the UC Global Health Institute, the former chancellor of UCSF, Dr. Hailey DeBoss, who's going to make some comments.
Thank you, Pat. Good morning, everybody. Chancellor Katehi, members of the UCGHI board and leadership committee, our keynote speakers, Drs. Jonathan Samet, Andy Hargerton, and Jonas Mazet, and all of you inspiring students from all our 10 campuses, esteemed colleagues, ladies and gentlemen. It is with great pleasure that I welcome you all to the 4th Global Health Day, where faculty, students, and trainees from all of our 10 campuses showcase not only their work in the evolving and exciting field of global health, but also how they collaborate across the 10 campuses and across many disciplines in both health and non-health sciences. On behalf of UC Global Health Institute, I'd like first to thank Chancellor Katehi and the UC Davis faculty and students for so graciously hosting Global Health Day this year. Each succeeding year, Global Health Day has been better than its predecessor. And this year, we expect no less, thanks to the incredible work of the remarkable global health planning team led with this unbelievable woman with incredible, inexhaustible energy and dedication, Dr. Patricia Conrad, together with Dr. Mark Schenker as her co-chair, and the student subcommittee that was already alluded to. Our thanks also go to the One Health Institute, which has been most helpful. I also want to acknowledge Dr. Lair Moore of the School of Veterinary Medicine, Dean Kural of the Graduate School of Management, Dean Freischlag of the School of Medicine, Dean Hillreth of the College of Biological Sciences, and Dean Dillard, College of Agriculture and Environmental Sciences. The support of leaders in the various campuses especially provides great encouragement to UCGHI and validates its work. Thanks also to Catherine Lee, the UCGHI program manager, and her assistant Rahwa Naguse for their incredibly hard work and organizational skills. Let us give all of them a hand. I now want to recognize two friends, both great global health leaders, not only in UC, but worldwide. Dr. Stefano Bertossi is recently been appointed Dean of the UC Berkeley School of Public Health, and I welcome him most warmly. Steph, get up so we can see you. Stand up, Steph. Dr. Jaime Sepulveda is the Executive Director of Global Health Sciences at UCSF. He's my boss, so I better behave. And I want to take this opportunity to officially thank him and UCSF Global Health Sciences for providing home for the core administration of UCGHI. I also know that Jaime has just been elected Fellow of the American Academy of Arts and Sciences, bringing honor to all of us and to the University of California. Jaime, congratulations. Finally, I want to welcome a longtime friend and an esteemed colleague who is in attendance, Dr. Marcy Greenwood. She was the former president of the University of Hawaii. She was the former provost and senior vice president of the University of California. She was the former chancellor of the UC Santa Cruz. But most importantly, she has been part of this University for over 10 years as distinguished professor and also as the Dean of Graduate Studies. Marcy, we're happy to have you back from Hawaii. The UC Global Health Institute was formally launched in 2009 after 3 years of planning that involved hundreds of faculty and students from all 10 campuses. It has survived the harsh economic times, and it has flourished thanks to the work of its 3 centers of expertise: One Health, led by UC Davis and UC Riverside; Women's Health and Empowerment, led by UCSF and UCLA; and Migration and Health, led by UC Davis and UC San Diego, and now UCLA. Together, these 3 centers of expertise have obtained over $28 million in research grants directly, and several times that indirectly by supporting other programs. They have developed several multi-campus undergraduate and graduate online and blended courses, helped develop a new Masters of Science in Global Health program at UC Riverside, and are continuing to plan a multi-campus Masters in Global Health program. They have organized many inter-campus symposia, colloquia, and workshops. They have developed several fellowship programs, notable among them the multi-campus, multidisciplinary GLOCAL mentorship program in conjunction with the Fogarty International Center at the NIH, the NSF-funded IGERT program at UC Riverside, which is producing water scientists and scholars for the 21st century, the Lo Sonki Health and Humanity Fellowship at UCLA, the Journalism Summer Internship at UC Davis. They have developed many faculty and student fellowships. They also have several significant global partnerships in Africa, in Asia, in Latin America, and Europe. You will agree with me then that UC Global Health Institute is delivering on its promise to serve all the 10 campuses and is living up to the concept of the power and promise of 10. UC Global Health Institute also follows the growth motto that appears in every IOM report that says, knowledge is not enough, we must apply. Willing is not enough, we must do. Finally, before I call upon Chancellor Katehi to make introductory comments, I want to express our collective thanks and appreciation to President Janet Napolitano, who will be here later on this morning to deliver the keynote address. Enjoy the 2014 UC Global Health Day at this beautiful UC campus, and thank you for coming. And now, Chancellor Katehi, it's my honor to call upon you, but first I want to thank you for the wonderful reception we enjoyed last night at the Chancellor's residence. Thank you very much.
Thank you so much, Haile, and good morning to all of you, and welcome to UC Davis. This is a great day. We are celebrating Global Health Day, and we are so pleased to be the host for this year's celebration. On behalf of our faculty and staff and students, especially those who have participated so greatly in organizing this event. I want to welcome you. It is an important day for the university because it really highlights the importance of educating our students and working into solving important problems around the world. And of course, health is a critical problem that we all face, not just locally in our own communities, but as we look around the world and we feel the connectivity today between us and even remote communities in Africa, it makes it even more important that we understand the conditions that make people healthy. We have a number of speakers today that will cover this topic, of course, and I'm looking forward to listening to what they have to say, and of course forward to the videos that our students prepared for the competition. It is a wonderful event. I have participated. This is not my first time in an event like this, but I have to say every time I come to an event organized by the Global Health Institute, I see more and more people. And that implies that the community around this activity grows. The interest, of course, grows, and our students find this area more and more interesting to them, but also more important in terms of the impact of their work. As we find ourselves more and more connected with the rest of the world, then our students become more and more interested in asking the questions on how the world, or the rest of it, really responds to the major needs we all face: food, health, poverty, connectivity, transportation, communication, energy. These are the top 10, if you put them together, great, grand challenges, I would say, that we all face. But those challenges are not new to us, obviously. We always thought that these were important to our society, but what makes it different today is that we've learned that learning about others is as important as it is learning about ourselves. I was in China about a week and a half ago, and when you travel to far places, then you see how close we are, because the issues there are very similar to our issues here. And when you start looking at food, for example, as a system, or health, population health as a system, then you realize how close we are, how important local conditions in one place then become to another place. We are not isolated. We are not secured from other conditions and other problems. We need to be engaged with the people around the world to try to address this problem so we feel secure ourselves and safe. And that is what programs like that teach our students. In response to the need to become more global, not just in our education, but also in our research, in our outreach, in our thinking of the problems we as an institution can really participate in solving. UC Davis is has been taking recently 2 major initiatives. And the first one is a global food center that we established in the process to think of food as a global issue, not as a local one. But the moment you start talking about food, then you realize it's not just an isolated system. You cannot speak about food without speaking about health. And then what really happens when you start talking about issues globally, you find out that the boundaries between these two systems are really non-existent. There is a tremendous correlation between food and health. So ideally, if you truly want to solve the problem of food and health, and eventually energy, and eventually solve the problem of poverty and social stability, that you really need to look at the connectivity of these systems. So what we found as we started developing the World Food Center is that health becomes such a critical part of it. So now we're very interested, of course, in taking the next step and looking at creating a similar initiative in the area of population and global health. And while in the World Food Center, we started with the concept of having a policy institute rather than research or education, because we have a lot of these among our 10 UC campuses. So we thought that the policy institute will be far more important in food. But in the area of health, we think that an educational unit will be far more important before we start talking about research. And so what we are going to be doing in the next few months, and we expect to see a lot of collaboration between our colleges of veterinary medicine and the School of Medicine, and of course the faculty in these two colleges and the faculty in other colleges that have an interest in population health and global health. We see a lot of collaboration between these individual faculty and their students and their deans to create a plan, a blueprint for a new School of Population and Global Health. And we hope that eventually that will not only remain at a postgraduate level, but will also start addressing or providing opportunities for education at the undergraduate level whenever we are ready to do that. But I personally think that our campuses need to pay serious attention to global issues in everything that we do. So for us, of course, UC Davis being the one agricultural school where we started as the farm, as you know, the farm for the UC, and being true to our traditions, food and health are very critical for us, and these are the areas that we'll be spending a lot of attention to. So with that, I wanted to welcome you to UC Davis. I'm really, truly looking forward to what I'm going to learn. I'm an electrical engineer, as you may know, or you may not. I have a lot to learn about food and health, but every time it's extremely exciting to learn all of these new things that our faculty and students are presenting to the rest of us. Thank you so much.
Thank you, Chancellor Katehi. So we're moving that because we were concerned that you all over there might not be able to see the stage. Everybody can see now? Good. Thank you so much, Chancellor Katehi, and also for your remarks, as well as for your continued strong support of global health. We really appreciate that. So next on our program, we have the honor of hearing the plenary talk by two of our outstanding faculty leaders here at UC Davis, Dr. Jonna Mazet and Dr. Andrew Hargadin. And so while they're coming up, I think I'd like to give you a little background on these two outstanding young people. Or they're young to me, okay? So first, Andrew Hargadin is the Charles J. Soderquist Chair in Entrepreneurship and a Professor of Technology Management at the Graduate School of Management here, just next door. He's also the Faculty Director of the Child Family Institute for Innovation and Entrepreneurship. He received his master's degree in mechanical engineering and his PhD in management science and engineering from that other illustrious university, affectionately known as the Farm, Stanford University. And his research focuses primarily on processes of innovation and entrepreneurship, as you'll hear about today. And then I have a great honor also of introducing my colleague, Dr. Jonna Mazet, who is the Executive Director of the One Health Institute in the School of Veterinary Medicine here at UC Davis. The One Health Institute focuses on global health problem solving, especially infectious disease and conservation challenges. Dr. Mazet is also the PI and the global director of a $75 million viral emergence project known as PREDICT, that's part of USAID's, that's the U.S. Agency for International Development's Emerging Pandemic Threats Program. And I'm very proud to announce that this year, Dr. Mazet will be inducted into the National Academy's Institute of Medicine. So we're very proud of that. So what they would like to tell you about is how breakthroughs happen.
Thank you. So we flipped a coin and I lost. To be honest, I am absolutely delighted to be here. It is among a group of people I don't get to spend nearly enough time with because I am over at the business school. But that said, it's great to be here and on stage with Dr. Mazet. We're going to do something exciting, at least for us, because we've never done it before. It's a dual presentation, and in fact, what we'll be doing is going back and forth between our various research projects and attempting to find in the two of them something interesting and valuable. So with that said, I want to welcome Jana to the stage with me, and now I'm going to drop very quickly into my research and give you a little bit of an introduction into it, and then I'll hand over the mic. So I study innovation, and I study it in two ways, both historically, looking at sort of grand sweeps of history and the innovations that changed that sweep, and also looking at companies, both large companies and small companies, and also particularly in the last 10 years, scientists at universities attempting to commercialize research. And what I want to talk about today is a research project I recently completed that completely changed my understanding of innovation, and particularly the central activities in innovation, why they were important. So with about as much fanfare there as I could give it, I'm going to talk quickly about this, which is the development of penicillin. Arguably the most profound innovation in medicine and perhaps in all of civilization in the 20th century. And I used to say that with a certain amount of hyperbole, but in fact, I gave this talk to the University Retirement Center a couple months ago. And at the conclusion of the talk, a 94-year-old man came up to me, and he said he remembered the first day that penicillin came into his hospital, and the first patient he ever treated with it, a woman, a 16-year-old with lobar pneumonia, who was essentially doomed to die in about 4 weeks once the infection took over her entire body. And they injected her with the penicillin and came back the next day, and she was perfectly healthy. Now, obviously, they overdosed her with penicillin because they didn't know the doses at the time. But the nice thing about penicillin was that didn't do any harm. But following her were two nurses who then told me about their stories of the first day penicillin came into their hospitals. And as I thought about it, I realized we remember when Kennedy was shot, we remember when we landed on the moon, but very few other days stick out in the minds of so many of us professionally that we would remember them in such a way. So this was a profound innovation. And I want to talk about it particularly because of the profound misunderstandings we have about it and what we can learn if we think about it differently. So most of us know penicillin from this story. Alexander Fleming in 1928 was culturing the Staphylococci bacteria in petri dishes. He was not a particularly hygienic scientist, and he left some dishes open. He came back several weeks later, and as he was cleaning out the dishes, noticed that a blue-green mold had prevented the growth of the bacteria in one of the dishes. And through a process of serendipity, sagacity, and luck, he recognized that, in fact, there was a mold that had bactericidal properties that could actually kill the Staphylococci bacteria, and therein discovered penicillin, bringing us this world, this groundbreaking innovation. And what's interesting about that is not simply that the story is completely wrong, but also that, that we are willing to live with that wrong story for so much of what we do and what we think about innovation. So let me give you a brief history here of innovation in penicillin. In 150 BC, we know that Persian soldiers used to carry moldy breads along on campaigns to rub the mold into wounds to prevent infections. So we already know that molds had some antibacterial or some infection-fighting properties. In the 1870s, the European scientific community, including Pasteur, Tyndall, Lister, and others, Joubert, all recognized the antibacterial properties of molds. They, in fact, actually recognized the antifungal properties of bacteria. And there was a review paper written in the 1870s that coined the term antibiosis to describe how this was a constant battle between two species for the same nutrient sources. In 1897, a French doctoral student, and I hate to say this for the students in the crowd, a French doctoral student isolated the penicillium glaucum and showed that it cured typhoid and E. coli bacterial infections in guinea pigs. And he published his dissertation, and nothing happened. You're in good company. In fact, let me jump right ahead there. And then in 1927, the year before Fleming's discovery, a Costa Rican doctor published in a French journal how he was using penicillin to treat his patients. So here we have 1929 when Alexander Fleming publishes his famous paper and comes up with the idea of penicillin and changes the world. And yet we have roughly 2,000 years of history showing us that we were already aware of that. Why, in fact, did it not, well, and then what happened was nothing, actually. Nothing happened for 10 years. And one of the reasons why, it was a wonderful note he wrote about his presentation at the St. Mary's Research Hospital to his colleagues: no questions, no interest. Nobody did anything with his research, essentially. And one of the reasons why was because his research wasn't on the discovery of penicillin. It was actually on the use of penicillin to isolate the bacteria thought to be the source of influenza, which turned out to be a virus. But B. influenza, it was very hard to culture that because of all of the other bacteria growing in petri dishes if you swabbed somebody. And penicillin was a wonderful way to kill all the other bacteria and just isolate the bacteria B. influenza. And he published his paper on exactly that, which is in many ways why nothing happened. What was interesting then was what did happen, because obviously we know penicillin came about. And what did happen happened because of this man, Howard Florey. Howard Florey was a Rhodes Scholar that came from Australia, but essentially by the time his career reached its apex, he was called back to the Oxford, the Dunn School of Pathology at Oxford, and built up a team that, simply put, in 1939 began studying penicillin as a therapeutic, and in 1941 finished clinical trials, human trials on 6 individuals, and managed to convince the US pharmaceutical industry to pick up and put their full weight of resources, including the US Department of Defense, behind the development, the commercial development of penicillin, the production of penicillin at scale. And that is why we have penicillin, and that's what we know. So before I tell you what lessons I learned from that by studying that, I want to hand it over, because what's interesting about this story is how you can see it unfolding in the innovations today in medicine, and particularly Jonas.
So that was very kind and nice, but we tricked him. So we brought in somebody from the business community to teach us some lessons, but really, I need the lessons now. I can't wait 2,000 years, right? And so we need it now, so I'm gonna actually put you on the spot to some extent in this and try and get you to help us do this better from what you've learned. So hopefully that will still be nice and pleasant conversation. So sometimes I'm too sassy. You guys can wave me off. So this is where I work. It's in color, it's now. It's modern, but maybe not as modern as we like to think about here. So in this part of East Africa, we think about how those cows and that woman is getting her drinking water, washing her baby, and what else might have been there that morning. And does she have access to penicillin? Probably, but she can buy it. She has to walk maybe a day to get it, but she can buy it, but probably without a prescription. She doesn't know if what she's using it for is the right thing. She may be giving it to more than just herself and her baby. She may be thinking about calves and goats and other things for which it might work and might not. So although we have had these breakthroughs, we have improved our systems. It's really improving the systems for people like us sitting here in this room. And what have we done on the global scale? So that's where I think we'd like to set the tone for today and figure out what we're doing with all this knowledge, and how we can shrink that timeline, certainly from 2,000 years, but even within our lifetimes, as we saw in your example. So I think we should just, by way of introduction, talk a little bit about what's going on in these places. And many of you in the audience are much better experts at some of these diseases than I am. So I'm just going to touch on these a little bit. But this is my friend Mzee Salendu. He lives in that community where you saw that woman getting her water. He died of extrapulmonary tuberculosis. We don't know where he got it, but likely he got it from drinking unpasteurized milk. Those are some of the women in his household. He had 4 wives. And when I first visited them, they told me that they boiled their milk. And then later, after hanging out with them, they offered me milk straight from the cow in that gourd that you see that she's collecting it from there. And it's not just the cows that we need to think about, but all of what the cows are exposed to and what those folks are exposed to. I put the lion because he's pretty, but you can see HIV there. It's a big problem in this community. And then what does that impact have on TB? And are we thinking about human TB, animal TB? What do we need to do? And how do we diagnose that? And so I know many of you, including our team, is working on that. But again, worth talking about when we think about HIV, that it took at least 50 years, maybe thousands of years, depending on who you listen to start to recognize that big pandemic that we all remember in our professional lifetimes. Well, maybe not the students, but most of us remember in our professional lifetimes. But we know that one. We know at least 50 years before that pathogen could have been known, right? And so what are we doing? What are we doing? We seem like we're still on the same timeline as we were for Fleming and those who came before him. And SARS, I think many of you know about SARS, and we were proud just a few months ago actually to publish a paper that showed the host of SARS is likely a horseshoe bat or another bat, but we found the actual receptors in those bats that could allow that virus to be transmitted directly to humans. That's 10 years after the outbreak. Again, that is terrible to me. 10 years it took us to do that. So while we're proud of that discovery, it gets you a good paper, is anybody going to use that paper, right? And we come back to how do we do a better job at making sure we're doing this on a time scale that works. And right now, some of our team are responding to the Ebola outbreak in Guinea. And in the neighboring countries surrounding Guinea. This one we've known about for 40 years, probably been around much longer than that, but we've known, and it's been causing outbreaks where we've been able to diagnose it for more than 40 years. And so what are we doing to shrink this timeline? That's where we need you. I think both in academia, we need to think better about business, and we need to think about how we're writing our papers, and we need to think about what we do when no one uses them. Right? So we can't just sit in our office and say, well, I wrote the paper, that's my job, that's how I get evaluated. We need to think about how to put these things into use when we find them. And so now I think I'll just go briefly back to this situation that I'm talking about. So all three of those examples, the HIV, the SARS, and the Ebola, those are all what we call zoonotic diseases, things that are shared between people and animals. And so when we think about the green areas of this graph, we think about what might be the pool of pathogens that are out there. And I'm going to focus on viruses because it's more what I do. But we think about that pool, and we think about how hosts are likely not, if they've evolved with their own flora, they may not be able to be infected, or they may not get sick. So we may not see disease. We may just see them as their normal flora, but it's that spillover. So what's going on when we see that spillover into domestic animals or into people that allows these epidemic curves, if you will, the big blue one and the big red one, to get out of control? What allows these things to amplify and spread, and how do we control that? And whether it's going to spill over directly from one species into humans, or whether it's going to spill from one species to another species, from bat to bat, and then to cow or camel, as we think about when we think about MERS now, and then into people. And so how do we get in front of that curve? And so that's really, we need your help, because just 4 years ago, my team responded to an outbreak of mystery disease in Uganda. This is at the Sudan border, northern Uganda, very rural. In fact, when we were working with the Uganda Ministry of Health, we had to talk to them and say, you need to go out there, because they weren't even really aware of where this place was. They actually took a trip, got to the end of the road, and turned around and came back and said there's no village out there, because they didn't keep going when the road ended. Okay? And so because of that, and because the folks that were there, so the NGOs and the people like us from universities and foreign help, aid, who were showing up, we still weren't that great at figuring out, and we still aren't that great at figuring out mystery illness. So it took weeks for people to get there, and then months for this thing to get diagnosed. And the sad story that I have to tell you was not an emerging infectious disease. This was yellow fever. And by the time we got out there, got it diagnosed, it actually had to, the sample ended up having to be shipped to the US, had to be actually deep sequenced at CDC before we recognized yellow fever. What did we do? Then all the aid organizations come together, spend a lot of money on a yellow fever campaign. Guess what? After it was over, the people were already dead, frankly, or recovered. And so there was nothing really to do for that vaccine. Maybe it'll help prevent cases in the future, but the outbreak itself was over, okay? So we're wasting money, we're wasting time, and we're not really helping folks in that situation. And so that's what we need to get better at. One of the things, for those of you who are clinicians, I'm a veterinarian, that are out there, one of the reasons this didn't get diagnosed is because we use systems, we train ourselves in differential diagnoses. We need to do that. It's the smart, efficient thing to do for most diseases, but we need to broaden our thought processes beyond that and say, when we don't know, when we don't have a good idea of what this is, we need to put some other things in place. And so we want to talk about that and how we might be able to rapidly change those processes. This one, yellow fever, yes, not seen in Uganda for 40 years. So there was no practicing physician in Uganda who had ever seen a case of yellow fever in Uganda. Their Viral Research Institute and Diagnostic Center was actually established for yellow fever, but no tests were still available. Nobody knew how to run them because all those people were retired or gone. Okay? Yellow fever also doesn't make you jaundice in this part of the world. And so if you were reading a book trying to figure out what to do, you wouldn't probably try yellow fever on your differential diagnosis. So the differentials happened about 3 times. On this, we made lists, we submitted tests, and those tests got sent off. Takes weeks, right? Because somebody's got to ride a bike to a car to this to get those samples out and wait for those results to get back while people are dying around you. It's horrible. Right? So we need to do that a different way. And we need to get to this place where we know what we're looking for, because we can now know what we're looking for. We can relatively inexpensively know what we're looking for. And we need to reduce those curves, those blue and red curves, down to something that's more practical. So I challenge you, sir. Okay, so my challenge, and it's a challenge we received from the federal government here and the international community, is how are we going to do this? How are we going to preempt or combat these first stages of emergence so that we can get to a quick response to mystery diseases?
I'm shocked.
Sorry.
Fortunately, I carry slides with me. But I will stop and say this is why I really enjoy this. This is so much more. This is the best part of my job. It is not talking about how to develop the next iPhone app or the next shampoo or dog food that sells better than the old one. These are real problems, and they're in fact real problems. But part of that is underlying this central challenge, because when we think we find solutions to real problems, we think we've done the job. We think that's all it takes. And, and therefore, when people tell us that Fleming didn't discover penicillin, we say, absolutely, that's true. And we wonder who did discover it, because clearly it was a discovery whose, and the idea itself was sufficient to change the world because it was such a meaningful problem. And in fact, it is so rarely, if ever, that case. In fact, to be honest, I'm simply giving my academic hesitation on that one. I have never seen the case in which an idea by itself did anything. And so let me start with, I happen to have 3 lessons in my back pocket that we can draw from the penicillin case. And now we can have a conversation after that about how it applies to how we would think about developing an innovation like this, and how we might recognize and reward the activities that are central to it. So the first lesson is an easy one. I already gave it away. It's not about the idea. We know that. We know 2,000 years worth of recognition that molds and funguses have these antibacterial properties. And in fact, we knew from 75 years of the European scientific community studying this that it was not even a novel idea to see it as a therapeutic in the medical sense. But really, that is a lesson that only raises more questions. If it's not about the idea, then what is it about? What are we doing? What are we as academics doing? If it's not about publishing the paper, if it's not about having that brilliant insight, how are we changing the world? And that's where it gets, I think, as an academic, very interesting. But it also gets very serious. Because fundamentally, what it comes down to then, if it's not about the idea, is very simple. It's about commitment. It's about turning that idea into a reality, and it's about recognizing the commitment that you need to make if you believe in your idea, or if you believe in somebody else's idea, the commitment that we all individually and then collectively need to make those ideas real. And I'm embarrassed to know I did not know the mission statement, that knowledge is not enough, we must apply. Willing is not enough, we must do. That is at the core of innovation. In fact, quite simply, I would say it's not innovation until we do it. And nobody cared who Alexander Fleming was or what his ideas were or when they were published until Howard Florey made penicillin a reality. So really, the idea doesn't even exist truly until somebody else goes and makes it real. I'll give you a quick quote. Larry Shepp, who's a mathematician who was famous, he has his own theorem named after him. He was asked by reporters why he thought he should have the theorem named after him when these two other mathematicians had already developed those proofs and published them. And he said, well, that's easy. When I discovered it, it stayed discovered. And we need to recognize that. You know, all of the good ideas in science are out there, but they're not really discoveries until they stay discovered. So let me just give you a sense of what commitment means. Alexander Fleming in 1940, after the first human trials were done in Florey's lab, Alexander Fleming acknowledged, he said, penicillin broth, that as he had it, was used in a few cases as a local antiseptic, essentially rubbing it on a cut or a scrape that looked like it was turning red. And although it gave reasonably good results, the trouble of making it seemed not worthwhile. Now, this is an absolutely wonderful statement for a researcher like me, right? What does that mean? You know, what do you mean by not worthwhile? Saving, reducing the scourges of staph infections and pneumonia and probably the leading cause of death in the US at the time and in Europe from bacterial infections. That's not worthwhile? What was not worthwhile? And that, when you pull on that thread, gives you a very good understanding and a sympathy for what is science, and particularly what is the path through science to innovation. And so what I want to talk about in penicillin is actually a commonality that I need to thank particularly my friend Bruce Hammack for, as he explained to me the challenges of developing innovations from science. And that was, here are the uncertainties that face almost any scientist looking at a medical innovation, particularly drug development. The first of which is we can recognize millions of, or hundreds of thousands of metabolites or compounds in the body or in food that we know are active and beneficial ingredients. But then the first uncertainty comes in. We don't know if we can actually isolate it, identify it, isolate it in quantities enough to study it. And if we can isolate it, is it stable enough to study? Most compounds, in fact, break down in the body, and for good reason. So the second uncertainty, if we go to all of the trouble to identify and isolate it, will it remain stable enough to study? And if it is stable enough to study, will it actually work? Meaning, will it have enough of an effect without having so much of an effect as to be toxic? And it is in that window that drug development has a great deal of uncertainty, because anything that has an effect, as a pharmacologist will tell you, will also become a poison in the wrong dosage. And if it does have an effect, can we make it in quantity to actually run larger trials on it? And if we can make it in quantity to run larger trials, will somebody else, if we're successful, be willing to invest and commit the resources to making it in commercial scale? And now we've just shifted to others, and particularly the private sector, who is then going to say, well, yeah, but if we make all of that investment in building it at commercial scale, will somebody come along and synthesize it, and all of our effort will go to nothing? Those are the uncertainties that faced Alexander Fleming, and it faced Howard Florey, and anybody else pursuing penicillin or any other drug for that matter. And they're the same uncertainties that face all of us. Can we succeed? Is it worth doing this? Now, Fleming, in fact, his best work was in lysozymes. And what he did was, when he looked at penicillin, he thought, well, all of these uncertainties are too great. I'm going to continue my existing work where I'm making great progress. Lister, he had the same idea, and he had opportunity costs, and he decided to pursue essentially hygiene. And he reduced the surgical death rates by 50%. Pasteur, pasteurization, and other things. Everybody looked at that and saw other opportunities that had more certainty. So the challenge is not simply making a commitment, but it's making a commitment in the face of uncertainty. Not knowing whether all of our work, whether that's our entire dissertation years or 5 years of our lab work, will go to nothing. Because any of these things might go wrong, or they might all go right, but somebody else comes out a month ahead of you and takes it further. So these are the uncertainties that stop commitment. And so it's not simply saying all you need to do is commit. It's, in fact, managing the commitment process in the face of uncertainty. And it's not simply that we need to commit ourselves, or perhaps easier, commit our doctoral students to pursuing these things. We need to not only build commitment in ourselves, but we need to build commitment in others to make this a reality. Because the third point I want to make in this is that the network itself is the innovation. It's not the idea, but it's the network of commitments that we build around the idea that turn it into a reality. And that is the central activity of innovation, is building that network. So let me give you a quick example of this. So first, there's our lone doctoral student, Ernst Duquesne, who, in fact, tried to publish his paper, but the French medical journals wouldn't publish it because he was too young. He ultimately ended up, after finishing medical school, he went into the army and he died 7 years later of tuberculosis. There's Alexander Fleming, who developed his recognition of penicillin. And then there's Howard Florey, 10 years later, who came to Oxford as a Rhodes Scholar. His roommate was John Fulton. I'll bring him back into the story in a second. While he was in his early career as a biologist and pathologist, he studied. He took grants. He constantly looked for grants that would allow him to travel. And he traveled Europe and he traveled in the US, meeting and working with other doctors from various fields. And in a particular case, he met this man, Alfred Richards, who was a pharmacologist at Penn State, which factors back into the story in a second. So he's brought back in the apex of his career, as I said, to Oxford to run a group at the School of Pathology. And there he decides, in fact, he insists as part of his hiring package, that the future of medical biology lies in biochemistry, which is an emerging field in the 1930s, and he insists on having the right and the ability and the funds to hire biochemists. And he goes out and he hires two of the best biochemists he can find, Ernst Chain, who was a theoretical biochemist, and Norman Heatley, who was an experimentalist. And he brings them to Oxford, and he builds, in fact, a team around them through the relationships he builds with the Medical Research Council of the UK, and particularly a man, Richard Mellanby. To understand what he did, Ernst Duquesne worked alone, Alexander Fleming worked alone. Howard Florey's team that he built before he began even studying penicillin shows his ability to build a network of people that he realizes were critical to moving the research forward. In fact, Gwyn McFarlane, one of the people in that picture and on his team, wrote later that Howard Florey recognized the limits of his own knowledge and deliberately chose as collaborators people who could supply what he lacked. In his published work, he had as partners a cytologist, radiologist, bacteriologist, hematologist, biochemist, and several specialized physiologists. Even in his early research, he was out building networks of commitment to him and in his research, their shared research, in ways that I think we should take note of. Long before you find that wonderful discovery that you think could become a reality, most of the work you need to do to lay the foundation for building a network should already be done in the networks you've built along the way. That said, that team develops then the early recognition of penicillin. They manage to identify and isolate it, build enough quantity to test it, first on 2 mice, then on 48 mice, and then on 6 individuals. Back at the time, it was actually relatively easy to find individuals available for human trials because the way sepsis worked was you had roughly 4 weeks after your diagnosis to live or essentially to die well. And doctors were willing to then acknowledge and share these patients with the Florey's team in order to see. And in each of those cases, the recoveries were miraculous, literally on the order of 24 to 48 hours. I can't imagine any of us will ever live to see science that gives us that much of a wonderful feeling at the beginning. But that wasn't enough to convince the British pharmaceutical industry to commit resources to developing it. And so what John Florey had to do was go back to the US, and particularly back to John Fulton, who was now head of medicine at Yale, and to Alfred Richards, who had moved from his position at Penn State into Washington, D.C. to be part of the US Council of Medical Research in the mobilization for World War II. And he reached out to them. John Fulton, in particular, introduced him to somebody, the National Research Council, Ross Harrison, who introduced him to the ag research labs, and particularly the man running it, who was a mycologist, a mold specialist. They introduced him then to the Peoria, Illinois Research Laboratory, where immediately, on the order of about 6 weeks, those people who had been working for the last 30 years on developing industrial scale production of molds for vitamins and other ingredients, were able to simply insert penicillin into their production process and immediately get roughly a 15x improvement in productivity. With that knowledge, again, he came back to DC, and through Alfred Richards, and his influence convinced the US pharmaceutical industry to commit the resources to develop penicillin on an industrial scale. In fact, it was his ability to commit, to get Alfred Richards to commit, and Alfred Richards' ability to then call in the heads of the pharmaceutical industries and tell them essentially, if you commit resources now, you will be able to license the production of penicillin. If you walk out of this office at 5 without that, you will not. So we will take whichever of you, are willing to commit, and will support you. It's a little bit of a simplified version, but it is in fact what happened. And that is the story of how penicillin took 2,000 years as an idea and 2 years to go from a laboratory team assembled to work on it into an industrially, a committed industrial process and production. And at that point, the numbers are staggering as to how quickly penicillin grew and became a successful drug. So I don't know where that, oh, I should come back to say, the one other explanation of why we think of penicillin, or as Alexander Fleming's discovery, is because his boss, Sir Almroth Wright, upon the first successful human trials, went to the London Times and immediately said, everybody should be aware that the discoverer of penicillin was none other than my own research employee, Alexander Fleming. And therefore, if you're thinking of investing any donations in further research, you should consider St. Mary's Hospital. A good dean, but a very dangerous precedent to set for how we understand how innovation happens. So with that said, let's talk about what you're doing.
All right. So I think, so you hand that back to me with a challenge of, I'm a scientist, I like ideas. And my eldest daughter, who's a woman now, with her tongue very strongly planted in her cheek, always says to me, well, Mom, you have a lot of ideas, meaning most of them not practical or useful. But I think it is easier, and for the grad students, maybe it's not the thing you want to hear, that it's not about the idea, but we still need to have them, clearly. But what I've found so far in my career that's been great here, about 15 years here at Davis, other places before, but what I found here is that my ideas, while I may think they're really interesting and innovative, usually someone else has thought about it. When I get in a room with smart people like you, people are like, oh yeah, I was working on that, or I thought about that. And so I agree with you. We can come up with a lot of ideas, and maybe we need to get over who had that thought first, who coined that term. We need to get past that in academia and just move forward and say, okay, what do we do with those ideas? And so the ideas that land use change, climate variability, markets and trade, all of these things could drive this emerging infectious disease. We think those are brilliant. We like them. They give you some good papers. But really, what are we doing with those? How do we adjust those? How do we get you all to work on some of these? Like, what is in climate variability and climate change doing to emerging infectious diseases? How do we encourage that network, I guess, so that we can truly have that innovation? And even though I never heard your talk before we started this project, I agree with you, and we've tried very hard with our PREDICT project that I introduced to you to say, okay, well, we all think we're smart, we all might have had that idea first, but let's get it together and do something about it. Let's have some commitment. Now, in academia, and part of when we talk about those guys, those old guys, part of it is funding. Right? So it's not just our commitment, but part of that uncertainty around the commitment is that we don't know if anybody will take it on. So we might spend the rest of our career working on getting people to take something on and not get them to take it on, and then what? We didn't publish a lot of papers, we didn't. So there's a reason that is reasonable behind that uncertainty. But I think you can make it work if you really say, no, this is the one. We need to bring the people together. So it's fora like these where we can start to stimulate some of that. And so with those ideas of the drivers behind where emerging infectious diseases come from, we can start to build the team that might have the commitment. And the lucky thing we had with the PREDICT team that we were able to build, some of whom are in this room and brilliant behind some of the different pieces, is that many of them were doing it anyway. They had the commitment, they were doing it for free. They were doing it without a big chunk of funding behind them because they believed in it so much. And I like to give a little plug to the wildlife people here because we do stuff on the cheap. So we're used to trying to scrap it all together and figure out a way, because nobody's really wanted to fund that, right? It's better to fund something that Big Pharma will pick up, right, later. And so I guess maybe even when USAID was looking at the people who were bidding on trying to get this done and the ideas, that's all we can really do is put forward the ideas in the group. When we write these proposals, as you all do in academia, I think they looked at it and said, these people look different. These people look different, and they don't look like the people that just write to us and get funding. They look like the people that, even though they just had a couple $1,000s, they were trying to make little chips away at this. And so I hope we can encourage others to think that way too. And so we look at probabilistic modeling first to try and help us target. So if I go back to that challenge, how do we make this happen on a global scale? We look at modeling to try and help us hone what we're going to do, and field studies, and those can be super expensive. You think about, go out to the whole world, find all the viruses that are out there, and then figure out which ones are important and might cause disease and might spill over to people later. And to do that, you need laboratory investigations. Where are the labs? And what labs are there? Because even when we have good labs, do they know how to do this? How many of you know how to submit a diagnostic test for an unknown disease? What box do you check on the form? How do you do that? We need to get to a place where we can do that. We can check that box. We can figure out how to do this. And so, so it's not just about the idea, it's not just about the commitment, it's about the network. So our models took us to the places that we think are the most likely places for emerging infectious diseases to start up. And those happen to be the best models we had at the time, about 5 years ago, happened to tell us that that's where population density is highest. That's where climate is coming together, sort of in the warmer situations, latitudes, if you will, and also where biodiversity is highest. So if the pathogens are going to spill over from one species to another because the host isn't going to get sick, but the next incidental species is going to get sick, then we need to look where that's happening, where those species are coming together in maybe a strange way or a different way than we've seen over the last couple thousands of years. So we started to build our network. So we needed the network not just for all those disciplines that I showed you in that sort of circular, we put together the models, so we need modelers, we need biostatisticians, we need ecologists, we need mathematicians, we need computer scientists to do that. And then we get out in the field, so we need field biologists, we need people who know how to get permits, know how to work with governments. Frankly, we need the governments themselves. We need people who know how to design telephone systems now that we have cell phones and access to that to help us identify when little blips of disease are happening. And then we need laboratorians in the labs, we need diagnosticians, we need virologists, we need microbiologists, we need epidemiologists, I hope, because that's what I am, to help design the whole thing. And then we need people to actually step back to the 30,000-foot view and look at it all and say, are we doing this right? And adaptively manage that situation. And when you do that, you end up with a lot of people. You end up with a lot of people. So just thankfully for the commitment from the funders that finally said, let's give this a go, we had to put together on the order of almost 400 employees. Maybe they only had 5% of their salary, maybe they had 100% of their salary, but about 400 employees to make that happen. And then you work in 20 countries and you start to bring in all the collaborators from those countries who may or may not, they're probably not getting paid, but they want to do it, they have the commitment. Why? Because they don't want emerging infectious diseases. They don't want to go to the hospital like I did for 2 weeks, 104 fever, nobody can tell you what's wrong with you. Nobody wants that, right? So we have to go to these places where we think these unusual circumstances are happening. This is Nepal. And these are the kind of interfaces where we need to look. This is it's an urban slum in Nepal, but as you can see, actually the animals and people come together in very interesting ways, and that whole system changes depending on political systems and everything else. So we need social scientists and behaviorists and economists to also predict what's going to happen there. So here in Nepal, we had no pigs. So we had, I don't know how many of you have been to Kathmandu. So it's an interesting place, right? Steers or cows just walk around on the street because you can't kill them, right? And you only need the girls for the milk. in the babies. So, so there's a lot of strange situations where you're just in the, downtown and there's cows walking around. So that's been happening for hundreds of years. So that's maybe we've seen the spillover that's going to happen there. But then the political system changed, and pigs, which never used to be in that system, came to town. Okay? So now we have the pigs coming from the hill areas, coming from different areas, mixing in with the monkeys and the jaguar and a leopard, actually, jaguar if we were here. But we see all these species mixing together and mixing together with domestic animals or semi-domestic animals like chickens and ducks, and we have the perfect storm, right? Oh, and by the way, how did they get rid of their dead? They burn them in the main river and then put the remains in the main river that is the river source for the city, okay? And this picture, I think, yep, this picture with the monkey there, he's sitting at the edge of the river underneath the funeral pyres, if you see those concrete spots coming out, okay? So everybody's mixing in a way that makes us worry. So this is one of the places where we would start to hone. Our models would say, look for these strange interactions of species. And that's where we're going to see when the environmental conditions come together in a perfect way, which may include social systems coming together in a strange way. This is where we're going to see these things happen. And similarly, if you think about in Gabon, people are starting to mine in caves to make our cell phones and get better products so your phone can be lighter. They're going to caves where people have never been before. There are species of bats that have never been seen by people before, and guess what they have? They have viruses that people have never seen before. What do people do when they start to mine in those kinds of caves? They bring whole systems with them, communities with them, so they can eat. They bring chickens and goats, and they cut down forests, okay? And so they're starting to mix with all the wildlife in that community. Again, the perfect kind of storm, the perfect kind of place that we need to look. And so we also have to do our homework as scientists, and we have to figure out where, if we're going to target, where do we target, and how do we target? So by history, by common sense, what kind of animals do well around people, what kind of animals adapt to these different changes, and what kind of animals are most related to us, so might share things that could be infectious to us. We can just by common sense pick the right targets, but we need to do the math and the homework and everything to convince everybody else so that they have the commitment to stand behind us that that's the right thing to do. So Dr. Johnson can tell me, but I think we have 3 papers now just on this, how to pick the right species, even though we already picked them because we could figure it out, but then the science shows us that we were right, thank goodness. So it's not about the idea, it's what we do with it. But once we get that, once we get those species and we get those locations, those interfaces, we get those countries where we want to go, we need to have laboratories. And we can't just send everything to the US and test it here. There are lots of reasons for that. It's not completely ethical, right? And so you can talk about Indonesia and flu and who gets to have the intellectual property, who gets to make the virus, the vaccine later if you move it around the world, those kinds of things. So there's lots of things to think about in global health. But also it's not building the capacity for those countries to deal with their own issues. So it's not the right thing to do that way either. And so I want to just give you the example of, again, the wildlife people being scrappy. This is where you could just stop and say, my commitment, my network does not allow it. I can't do it. It's going to cost billions of dollars to put laboratories in these countries to be able to look for new things. But this is my Tanzanian colleagues' innovative way to address this issue is let's just build a lab. I said, well, okay, our great deans sitting next to each other, Dean Emeritus and current dean, built a beautiful building with great lab and let us move into it. That building cost $90 million, right? We moved in last year. I love it, by the way. But I can't do that. I can't do that around the world. I can't help with that, right? They said, it's okay. We need a lab. We can make a lab work. And so they got 2 shipping containers. They stacked them on top of each other. We picked up equipment from different places, especially the other example in Rwanda. We walked around, and there's equipment on the floor, says gift from FAO, generous support from WHO, in cartons on the floor where people are cutting up chickens. Okay? Because the equipment comes, but no training for using that equipment, no maintenance or installation agreements for putting in that equipment. So there are scrappy ways to do these things. You don't have to say, I can't do it. You just have to find a way. And so we were able to put this lab together, a full viral diagnostic and research molecular lab with its own containment in case we find something super dangerous, its own electricity backup, its own internet backup in case the campuses goes down, which it does a lot, $40,000. Okay? So if you're scrappy and if you have the commitment, you can make it happen. And by the way, even though ours is nice, theirs has granite countertops and marble floors. Just saying. This is a picture just to prove to you if there's any molecular people in the field. In the audience, we have good compartmentalizing of all the different activities and good ventilations and appropriate standards and things. But not just the equipment and the space, you need to know how to do it. And if I go back to that yellow fever example, even when there are tests, if you don't know what you're testing for, you probably aren't going to get a diagnosis. And then for anything, when I gave you the challenge, anything that we want to pick up that hasn't yet been diagnosed, there are no tests. So the best thing we have and what we use here tends to be deep sequencing. That is metagenomics. You throw it on a very expensive machine with some very expensive people, including laboratorians and biostatisticians, and you try to pick up all the genetic material that you can in that sample and try to find out how high the copy numbers of that genetic material is and figure out if there's something in there that's new. Again, you still have to what we call blast it. It's a nice word. Blast it against whatever else has been discovered in the world and say, does it look similar? So if you're looking for something new, you may or may not find it. We took that concept, but we took it back to a technology, again, being scrappy, took it back to a technology that, frankly, didn't get utilized to its full value. So conventional PCR, not real-time PCR, not just going back to conventional PCR and saying, did we use this technique, which is now cheap, right? Within a few years became cheap because everything else, newer and fancier, became expensive. So we went back and said, did we use this technology to its best? And some of the brilliant folks that we work with said, maybe not. Let's come up with some of those old research methods using conserved primers for viral families. Instead of looking for a specific virus, let's look for a viral family. And once we pick up a viral family, we can sequence that. So we're sequencing now, not on the fancy machines, on more conventional, cheaper sequencers. We can sequence just those positives as opposed to every sample we might take and cut our costs. We could actually cut our costs about 90% from using those expensive sequencers. And we can cut our costs from going down the differential list, like I talked about before. We can cut our costs at least 40% even from that, just by doing conventional PCR for every viral family that's ever caused an epidemic or a pandemic. Okay? And you can do that, and if you're efficient and trained and all of those things, you can do that in a day. So it's not like it takes longer than doing the other technologies that are more expensive. So these are the viral families that we look for, and we had to have some other innovation. I'm throwing this in for you guys so you don't want to go away from here thinking, well, my ideas aren't worth it. I should just go do something somebody else did. We had to come up with some new ideas. How do you actually do positive controls? How do you get, you can't move a positive sample of Ebola around all these countries and say, here you go, here's your positive control, right? That would be very dangerous. I would be fired right away. So, can you fire me? I think you can. One of you can. There's a way, right? Yeah. Tenure and all, but still, I think you can. So we had to come up with some synthetic controls. And this is our first control. I think it has 12 different viral families on it. It has a very geeky little tag on it that spells out predict, if you like to mess around with these kinds of sequences, that tells us if we have contamination. So if we start to get positives from these labs, we can also tell that it's actually our synthetic control that we sent, but it's not dangerous. It's not infectious. So there needs to be that innovation that continues to go. So I guess the story is, I believe you. And whether it was the good idea or coevolution of good ideas and the processes of commitment and building the network. We were able to build that network. I talked about those people we employed, but we also worked with and trained over 2,500 people in the different countries that we're working. Those could be field biologists, veterinarians, epidemiologists, laboratorians, all these folks to start to do this. And they were willing and able. Because they wanted the same thing we wanted. We worked with 59 governmental ministries in these countries and continue to do that. Why? Sustainability, right? To get these things going in the future. And I'm pleased to say now that even though we're doing this for a research project to look and find those viruses, we also can find known viruses as we use these exact same methods. So we can employ these in hospitals now. And so some of the food and agriculture supported livestock laboratories, as well as hospitals and WHO supported laboratories, are piloting our techniques now because they have so many undiagnosed cases. And so it's not going broad scale. We're still evaluating, how well can this be done and how inexpensively can it be done, but we can spin it out. And we've just in the labs we've worked with, it's been about 35 labs, we've collected samples and almost tested samples from all of our 50,000 animals. And we found 250 novel viruses, actually a few more now, as well as many known bad actors. And we found those pathogens, the ones that we know already as pathogens, we found those in people that might have been of animal origin, but we've also found human origin pathogens in animals killing endangered species like mountain gorillas. So we have conservation implications. And so for today, I think we hope, the reason we're sitting here and not standing up and giving straight talks is we hope that you'll find new collaborations. You'll find ways to put your new and maybe not so new ideas into practice by working together, and that you'll think about One Health. You'll think about the whole side of it. You'll think about animals, people, and the environmental drivers for things that bring people together. And so that's our little One Health plug. You can attack these problems if you work hard together.
So I just think this is a fantastic project. So if we could just take a second to just say what a great job this is.
To you too.
No. I think that, all I wanted to say really there is, as I said in the very beginning, the things I have learned by studying the origins of penicillin and then other projects from a similar lens has been the skill set and the commitments necessary to make these kinds of things work. And they are truly remarkable. And as I said, nobody gets tenure for building a network that changes the world, and yet that is something remarkable that we need to appreciate. And so that's why I wanted to take a second there. The other thing I wanted to add on this is, you appropriately kind of pushed back, but very gently, so it's good. There is a very profound role for ideas in science, for new ideas in science. That is science. That is good science. It's simply not innovation in the sense of changing the world, of getting out there. It's not until those things become real and change the way we practice and the way we organize it. But that said, the other thing I want to say about, is getting out and making it real is not the end of the ideas. In fact, it's often the beginning. It's where the new idea, more new ideas come to innovators in the process of making it real, in realizing, well, we can't do it with the state-of-the-art equipment. We need to go back and continue innovating along PCR. And then 250 novel viruses you find in the process of doing this. You end up creating both new ideas that make the real possible, and then you find new problems that you wouldn't have found otherwise. I mean, that is the story of Pasteur and working on pasteurization. The germ theory did not come before his work. It came afterwards when he realized he needed to understand what was going on in trying to find practical solutions.
Just a little plug for our campus. He did that for beer and wine.
Exactly.
And so sometimes the commitment is for different things than you think it should be.
Exactly. Okay, so right now, unless you have another comment, we have questions. We have opportunities to take a few questions. There are 2 microphones up, but if you...
There's one right there. I think they want you to use the microphone for the audio-visual record.
So, is this on?
No, yeah.
Now it's on? Okay. My name's Craig Cohen. I'm at UCSF. This is wonderful, by the way. My question is in regards to the commitment and so forth, in regard to drug development. One issue that many of us rely on federal grants. And so those grants that we work, put our whole lives into, our teams into, then go through a peer review system. And nowadays, with NIH, for example, pay lines may be 10th percentile or less. So I wonder if you could discuss that, because we're obviously in building the team and the commitment, we also need to convince these external peer reviewers. And if you can give a comment on how well you think the system's working, are there alternatives, et cetera. Thanks.
Do you want to go first?
I'm going to let you go first.
Okay. Yes, so it's a big challenge, and I think we're past the days of he's too young to publish the paper, but there's still some issues there about how those reviews work and whether the people that happen to be sitting on the panel that time are the ones that could recognize that that's the brilliant one, right? That is worthy of investment. So it's an issue. I would say first and foremost, don't give up on those situations and trying to use them. But what we did, and maybe it's part of that scrappiness, that commitment, is say, these guys aren't going to go for it. You know, I'm still working on NIH. I bring them to meetings and try to work them so that they will fund those of you who might study the actual pathogen in the laboratory. It's not really working, I'll be honest. They may go for it eventually. There's a new center, looks like it might start up and it eventually might work. But what we did and what we tried to do on this campus is say, we need to find somebody else. We need to not be, so UC Davis and the vet school does very well with NIH. It's been our big, foundation. But we said, we want to do this new stuff, and they're not going to probably be new. I don't want to wait 10 years for them to come up. Who else is out there? And so we start to look at other funders that we may not have looked at before. So USAID, great on our campus for our ag part, but starting to look at them and say, hey, look, they might suddenly come into this realm. They pay for a lot of vaccine. They don't want to pay for vaccine anymore to send it out and have it not be useful. Just have it as a Band-Aid. So maybe they'll go in this direction. Newest to us is Department of Defense, really going after them. That hasn't been a big focus of our campus. It freaks me out. I'm a pacifist. I do not want to be a defense contractor, to tell you the truth. I'm sorry this is recorded, because they'll probably find out. But I
knew 10 minutes ago.
I'd rather have them spend it on this than on guns. So it's getting out of our comfort zone and having the commitment to look for other sources, and not stopping with those sources that should be the foundation of what we do and have been the foundation, but making sure we're looking at what else is out there.
So to that point, and I don't want to, the NIH, the NSF, these are part of our network, and part of that is an incumbent on us, not the individual scientists alone, but all of us, working in the universities to try and change how those people view the process and the end-to-end process. We teach a number of commercialization programs. We teach a number of programs that are dedicated to helping scientists, faculty all the way down to grad students, understand what they can do to move their ideas forward. And we have to find external sponsorship, because the NSF and NIH grants don't cover that. They won't cover the commercialization of the work that they're sponsoring. So I'm happy to fly to DC and help you anytime you want to go there and talk about it. But the other piece of it is, as John said, what made Florey successful? The Medical Research Council of the UK funded up to a point, and that was it. And the Rockefeller Foundation played an enormous role in early days getting him connected to other researchers around the world, and in later days getting him out to the US again and connected to all of these other people. And so there are other agencies that that you have to then go out and find who recognize the challenges and the requirements there.
Yeah, please.
Thank you for the brilliant collaborative presentation. I'm Dele Ogunsetan from UC Irvine. I was struck by Fleming's comment about not being worth it, and the issues today with neglected tropical diseases and very few people suffering from an ailment. There needs to be a different kind of incentive. I mean, the commitment is there, but I imagine that penicillin got that boost because the promise is there will be a large reward after the fact. So I want you to comment a little bit more about the kind of work that you're doing and the commitment of the government to keep this going despite the fact that there will be very few reward systems or commercial promise, and also what the innovation rewards are.
Sure. So if I could just jump in on the academic side on this one. So first off, Florey didn't see a dime. In fact, Oxford barely saw any attention and reward for the work they did. They didn't patent. They didn't believe in patenting. And lo and behold, it worked anyway. Most of the patents were in the process patents for commercial production of penicillin. So just to make sure that's. The other piece is to actually go a little deeper into what uncertainty means. There's a difference between that most people don't really appreciate between risk and uncertainty. Risk is flipping a coin. You have a 50-50 chance, a known quantity, a probability. And risk is defined by that knowledge. You're aware of the odds. You're aware of the bet, and you're aware of the payoff in risk. Uncertainty, you're not aware of the odds. You're not even aware necessarily of the bet, and you're not aware of the payoff. You don't know whether this is going to take a year of your life or 10 years of your life. You don't know whether the probability will work or not. And in fact, you may be successful, but again, as I said, be 3 months late, and there's no payoff whatsoever. But the thing about uncertainty that makes it profoundly different is it's about ignorance. It's not about knowing the odds. It's that you don't know what you don't know. And what Florey did wasn't leap in the face of the same uncertainty that Fleming had. Florey knew so many different people in so many different fields that when he brought particularly the biochemists together to look at the problem, they looked at it and they said, well, of course a biologist wouldn't solve this. This is a biochemistry problem. And to them, there was much less uncertainty about isolating and stabilizing the compounds. And that got him started. And then as he further and further built out his team, he recognized every time you add new knowledge, your uncertainty goes down, because to those people, it's not uncertain. If you find the right people, they've been doing this all their lives. And so when we think about uncertainty, it's not a common scenario for everybody. Some people are particularly good at reducing it simply by finding the right people or having confidence, that they will find the right people when they understand the problem.
And I think we're about out of time, but just to follow up on that, I can't really weigh in too well on all the neglected tropical diseases that we know about already, but except those that have periodic spillovers. I will say that because of this problem of not being able to attract attention and not be able to get people to produce treatments for those things that are affecting a small group of the population, we've tried to move upstream and say, all right, we don't want to chase every single pathogen that may affect a small proportion. We want to move upstream and figure out good measures to prevent the activity that allows them to become the next neglected tropical disease. So that's basically us, and having the luxury of not having that disease or not having built our career in that disease, we can say, let's try it a different way. And so that's why we've tried to go upstream. But it doesn't help the people that are suffering from those things right now, and that is a real significant challenge. I do think that continuing to try to find new networks and new ways to do it and not be constrained by this is always how we have to put these new treatments in place is a great idea, and together we can figure out how to do that better.
So I'd like to thank John Mazet and Andrew Hartigan. I think this is an excellent example of an interdisciplinary team collaboration in the presentation and how we go forward. So are you inspired? Yes. So in this room and across the 10 campuses of the University of California, we have tremendous ideas, deep commitment to health in California and globally. So now we just have to get out and do it. And that's what UC Global Health Day is all about. It's our opportunity to bring you all together, to network, to build those teams to solve these big problems.